compute the value and compare with the existing floodplain and say that the information, this much water level, if it is announced by someone, you can compare with your lookup table and say, nomographical table, you can say, this much volume will be there in that particular river at that particular gazing station. It is a kind of information that we can give directly just knowing the elevation there at any place in our reaches, especially at particular gazing stations. Remember. So that has helped us. Using this gazing station, one can calculate the wave celerity and the flow areas, okay, wave speeds and wave local velocities using the normal rating curve. So this lookup table I have calculated and used in the different varieties of bed gradients with roughnesses, and developed again checked the various parameters here, and the discharge and corresponding discharge stages also. From the discharge, we have computed stage. This is the beauty, another beauty of the VPMM model. If you compute the discharge, corresponding discharge stage can be easily calculated. Remember, so volume again is conserving. Efficiencies, you can see it is any hypothetical model which is more than 95 is allowed for, that model for the field problem. Remember that. Okay, don't say nowadays many people are doing a lot of research and saying that model is showing 75% results, so my model is best. So I oppose that. So any hypothetical analysis, what you do, you allow only 5% error, not more than that. Therefore, we stopped our comparisons at 95. Below that, we have not allowed. So 35.57 onwards, we have seen. Above that only we have seen. So below that, though we got it for a certain special cases, we have told that after 1 upon S naught del phi by del x, you see 0.6111 showing 95%. If I go further 1 upon S naught del 0.7, 0.8, so I cannot see 95.57% because there it will affect the nonlinear behavior of the 1 upon S naught del by del x. So water surface profile in a given reach. Therefore, a model has to have certain limitations and work under certain limitations. So that was calculated at 2 kilometer stretch, and this is calculated 12.5 kilometer stretch, and these are the results. Okay, you see the observed value here is St. Vannan, and this is the model. You cannot see the other model. Both are, two lines are inherent there. Any slightly deviation that coming is due to the particular prevailing conditions of the panel bed and the roughness. That's what you can see in that particular model. You see, triple 001 is the case where this model is crossing 1 upon S naught del y by del x is more than 0.5, which we have kept as a criteria, applicable criteria. Obviously, it may be 0.6 above, I think, here for this case. That's how the model computations is peak estimation. Of course, it is close to the St. Vannan's benchmark solution, but the computed value is slightly differing from this place. No matter, discharge is computing, but it is showing stage is a little higher, whereas for discharge it is almost same. So this error may not be caused more effect on the evacuation processes. These are the things. Next, performances. And 1 upon S naught del y by del x is explained more clearly. This is another situations I created. Channel type is not smooth now. We have created abrupt changes in the natural cases. Main channel, prismatic type, 2-stage channel we have created. Okay, we have named it as this one, right? Ecker's channel, right? Here also we have created different situations and worked out the different solutions. And the figures, you can see the efficiencies here. I have marked here, and you see at whenever the flood is reaching to the 1.5, you see the 1.5. You go to the 1.5 in the channel cross section. You see this flow depth main channel is now entering into the flood plains at this particular place. Therefore, there is a sharp shape of the geometry of a channel is there. There must be abrupt diffusion of the flood wave takes place. So in our model, which is showing that. See, here also you can see that. Here also you can see at this is waves and discharge versus flow depth at 1.5. I think this figure I have not plotted that. can see at 1.5, there is a jump occurs here. Okay, so at this particular location, you will see a kind of disturbance in the flood wave calculations because diffusion characteristics are coming into the flood wave. Remember, yeah, it is more disturbances due to the variation of the larger sub-reaches that we have maintained. Okay. Yeah, this is a special case we created. At 1.5, you see the diffusion. All of a sudden, there is a bracket. We managed here to bring the sub-reaches into more number of sub-reaches. That means we have reduced the del X. Okay, that's what I said. You cannot take 100 stretch kilometer. Here, you have to take the minimum distances, the sub-reaches, to maintain this nonlinear behavior in the flood process while estimating the discharge or stage. These are the performances. You see the results which are computed versus the observed. Mike 11 here I have used the lines which are the parameters, whatever computed, are falling closely on the 45-degree line, right? So with this one thing, this is the another concept explained on the natural channel for Antonio and Pontefelsno, Santa Lucia. The rating curves also we developed here using the similar model. Yes, these are the developed rating curves by me for that particular river. Okay, upstream and downstream rating curves. The model will allow us to compute the rating curves also. Yeah, these are the flood scenarios, natural flood scenarios. We computed and overlapped on the recorded observed values for a different flood events for the data which we have collected. So these are the peak estimates in a simulation mode, not in a forecasting mode. Okay, so you can see the even the for flood scenarios for a field problem, you can see the performance is observed for a synthetic channels. It is 98%. For if you see this table here, yeah, let me say something about here. You can see the results of the efficiency of the model. Here it is 99, 99, 99, 95, 92. Yes, in this particular model, it is showing 92.53, though it is a field problem. Okay, here it is 90. Of course, computed is, our routing model is discharge. So computed is a, after this from we are calculating the state. It's a derived quantity of discharge. But the routing is done only for discharge. That means you take this consideration into here. So 92, above 90, this model is performing better. For field scenarios, 10 to 15% of error people are allowing. You can take SWAT model, their efficiencies, etc. Any other Mike 11 model, field problems, people are efficiencies are limiting, maybe above 75, more than 90 also, but 75 also compromising. But our model, we stopped at this particular location. So for this particular scenario, we got a 92.5. That's it. Because that is a multi-peak flood. That's why. For everything, there is some reason. Otherwise, model will not behave like that. Yeah, even I applied for dam break during the dam process. I applied it for the inflows. You see the observed and the VPM methods. So we have tested the model with the dam break concept also. And the model behaving, you can see that VPMM is computing more closely to the observed values with the little deviation, but the peak computed values, if you see this side and this side, so it is little high. I told you that any model is having its own limitations. It cannot be applicable for all excellently, remember. It is having some limitations and considerations and approximations within which the model performs. So under that situation, the model has to be picked up for a particular field problem, especially. Okay, these are the limitations. I just know you told. So highlights, cross it. Another, this thing. These are the, yes, this I have compared with the SWAT mode. Recently, people are using the SWAT as a routing component. Their MCTP they are using. I used our model in the SWAT component and worked out the merits and demerits of the SWAT and our model. Okay, so using the benchmark solutions as HACROS. For taking space step as longer, space step 4 kilometers, space step of 1 kilometer, and though everywhere the model is showing eval is almost 0, but the model efficiency is also getting affected here. You see here, based on the roughnesses the time step, sorry, delta T variation, time variation. People are taking forecasting time interval is 1 hour, 2 hours, 3 hours, 24 hours, like that. So you see, while using the time interval and the space interval, people have to be very careful for physical problems, physical methods especially. So I wanted to show even my model a little bit I'm facing sometime, but I'm showing my model is showing minus 9.11 error at 24 hours time step, which is a longer lead time. Okay, time interval is affecting the model inbuilt derivations. Please remember this. Okay, these are the data. Yeah. Now I'm coming to that red is what you can see the VPMM model. All parameters, QP error, error in discharge, error in time to volumes. Almost all models are showing mass conservative excellently. But if you see the sum of errors that are cumulatively worked out for the high slope to the lower slopes, from 0, 0, 1 high slope to the lower slopes, because this kind of scenarios, probably these block box modelers are not applying. The reason is that they'll pick up the particular river flood, so there the particular river reaches that, so they will work for that and match their results with the observed values. But here I have picked up all characteristics of the river, steep to mild, from mild to the higher lower slopes, and created the similar environment and calculated all evaluation criteria and summation of error. You see now, summation of errors for VPMM is only compare the the bolded items if you see. So the summation of errors in the 001 slopes, the VPMM is performing better compared to the genetic algorithm and differential evolution and PSO and HS model. Whereas when we go to the higher side, even our VPMM is giving little higher summation of errors, but still compared to the other NN models, it is less. Okay, right. This is how the one is the calibration mode, another is the evaluation, the validation mode I work. This Reddy has taken only the genetic algorithm. He has used all kind of channels for only for genetic algorithm, estimated parameters k, theta, and m, routing parameter, power m, that is the routing equation. Okay, so that he has used only one genetic algorithm and compared the VPMM model. That's all. So these are the characteristics of the floods that are estimated using calibration mode and verification modes. You see the ANN here. This dotted line is the ANN model. This ANN is, it is having initial, what do you say, this kind of lag time is there. That is called ANN models will take warm-up period. So in warm-up period, you will not see any kind of establishment of discharges. That is why. So this is what is happening. So NN is not showing any information till 13 hours. So that is one of the drawbacks of that model. But still, when you are calculating it, the peak productions of that black box models are good. After that, go to HECRAS and Mike 11. Of course, this will be explained more clearly by my successor. So HECRAS approaches will be, we have to generate 1D and 2D also there. So this is 1D. You have to create geometric file wherein you have to create the cross-section information like this. Without this, you cannot run this software. This is the, how can you get the cross-section information at every 1 kilometer, at 5 kilometers in a river? Very developing country to have the surveyed data. That is the drawback of using these softwares. People should realize this. Okay. So if you have the data, then only you can accommodate that particular data as an input into that model and run it to get the results. So cross-sectional information is the main data, important data to run this kind of HECRAS, similarly Mike 11. This is the 2D flow that we have created, floods propagation on a particular river basin. I think Reddy also did this, I remember. So Sonareka, he has not done, I think he has done for Krishna River. Okay, so I did it for Sonareka only. with another research column. We could able to calculate the flow velocities and the depth and the distribution, spreading of the water on the basin in two-dimensional way can be possible nowadays using this. But whereas we cannot, in our VPM model, we have not developed to this type of user interface picture mode of applications, wherein we have to have GIS interface for this. Whereas in VPM conventional models, they don't require, they have not upgraded to that particular GIS-based interface. If we could upgrade it and link that as a component model, across using the kinematic MCT wave, KW, kinematic wave MCT model. So if we use a VPMM as a component model in the across and Mike 11, obviously, so ES interface and RIS remote sensing interface is easily possible, and that model will work better compared to other models, as I proved here in my results. Right? This is what the cross-sectional information in Mike 11 in hydrodynamic model I used. These are the cross-sectional informations supplied for the Tiber River. So this is our thing. We have calculated the discharge and the stage. You cannot calculate the discharge and stage at the same place. You will be calculating the discharge at the downstream side of the flow depth of corresponding flow depth at the upstream side. This is the one. You cannot get the same depth and same discharge at the same place. This is one drawback. At the same time, the river reach here, you cannot take del X value as a longer reach. Of course, you can calculate the discharge at 100 kilometers straight, but you have to discretize the river reach into small sub-reaches, 1 kilometer or 2 kilometer like that. If it is more than 2 kilometer or 3 kilometer, it affects your results, your peak values and computed values. So that is a very important issue because it is it is a grid-based approach, finitely different stream approach. So del X and del T have to be managed with the closer values. That's it. This is one example case. Yeah, these are the conclusions that I can draw from my work. The physically based models, always I suggest more better for the physical problem to solve, like floods or flood situations or physical problems. So physically based models will give better results than these nonlinear LM methods. As I proved you that summation of errors has proved that errors committed in physical model is less compared to these artificial intelligence models. That is one. And the other is that flood propagation ability and mass conservation ability and the peak reproduction is very good in VPMM model. And Mike 11 cannot produce the stage and discharge hydrograph information in the same location. That's what I already told you. And the stage discharge can be calculated by VPMM method. So preliminary investigations carried out with the considered objectives and routing solutions obtained using the longer routing. We are also still such ways and means to redesign or rederive this equation for maintaining the longer reaches to accommodating it. With this, I thank you all. I think I have taken excessive time, but this is required to explain everything, to bring the complete flavor to all of you. But questionnaire, I think, may not be good. I think for more people are there. If anyone want to ask me any questions, they are most welcome. They can write to me with my mail ID, or you can search me in my website, Institute of NIT Jamshedpur. Okay. So with this, I now first apologize Mr. Manish Kumar that I have taken his time, half an hour time. At the same time, I thank the organizers, especially my student Venkat Reddy and the coordinator KV Sahu and the tech coordinator KC Pandaji is the head of the department. Sorry, KC Pandaji, and the tech coordinator Chitaranjan Dasji and principal Dulu Patnaik ji. And above all, I thank all participants for very patiently listening to my views, whatever inventions that we made. Of course, I may be somewhere, not established fully, but to the extent time constraints, I pulled it in a short form. So derivation vagaira, I think I can share if you want to work with me. I'm very happy. If any question is there, one or two, I can answer without wasting much time. Otherwise, I will open for you all people to talk to me directly over the phone or any mail like this. Okay, now over to coordinators. Thank you very much.
Thank you, sir. Thank you, sir, for very wonderful presentation. I mean, covering almost all the approaches related to flood modeling.
Yeah, very good. Thank you, sir.
Hello,
Thank
sir.
you very much. Yeah, thank you, sir. Thank you
We
very
have
much.
some questions.
Yeah,
For 1 and 2 questions, and rest will mail to you, sir. And
yeah.
one is, what are the precautions should be taken for high-rise buildings before their construction in flood-prone area?
Actually, I'm not a constructional, structural engineer, first of all. Okay. Okay. So to answer that question, I think the structural engineer may answer well for this. But still, I can, in hydrological terms, I can try to answer that question. See, if you want to construct a structure near to your river basin, of course, many cities have come up. Many cities have come up, on the bank of rivers, remember, right? So they might be taking the soil bearing capacity is picking up at a suitable level, going to a certain deep and also considering the impact of water that is coming and the soil, the groundwater movement below the or beneath the structure. Say, for example, seepage loss estimates, seepage consideration they might be doing while designing in the structure. Okay, here seepage is the main point parameter while constructing a large structure. Of course, dam. Dam is also constructed on the bank, river itself, right? Even
Yes.
earthen embankments are constructed in the river itself. So we consider always the seepage, probably Levy's theory and the Koshlas theory. People might be knowing, those who are civil engineers, they might be using these logics and techniques to compute the seepage estimates accordingly. The pile foundation, fire foundation, whatever foundation is to be suggested, or massive gravity structure, whatever is to be suggested, they based on them only. So any structure which is in contact with water, retained structure, especially hydraulic structure, have to take care of all these seepage losses, seepage phenomena into consideration. Yes, I think though I'm not a structural engineer, in a hydraulic perspective, hydraulic perspective, I explain. Yes. Any other?
Sir, just another one is how to measure discharge hydrograph in ungauged stations.
Excellent question. This is a very good question. The ungauged, that's what I told you. The rating curve I have calculated. I already told you that this EPMM is able to produce the rating curve. Rating curve means it is the information of flow depth and the flow discharge information. Remember. So if you have, you cannot access any location. That is called as ungauged. Suppose forest, rivers moves through forest. So accessing forest zone and computing the flows, measuring discharges is difficult. You cannot establish, set the devices in the forest zone here because life threat is there. So what we do is here that the upstream information and the downstream information of the rating curves, we
Okay. Hello, sir. Hello. Hello, sir. Hello, sir.
Hello, sir. Hello.
Hello, sir. Am I audible, sir?
Correct. Understand?
Hello, Manoj.
Hello?
Hello, sir. Yes, sir. Right.
Yes.
Thank you, sir.
Yeah.
Yes,
Thank
sir.
you. And
too, sir.
rest of the questions, let me not eat the
Yes, sir.
time
I
of
shall
our
make
time.
it.
Okay. Because it's a one-day program, I cannot spoil the time. Thank you, sir. Thank you very much. First of all, especially I thank
Sir,
all
thank you, sir.
participants and the organizers. Thank you. Can I leave now?
Sure,
Can
sir.
I leave
Thank you,
meeting?
sir.
Okay.
Yes,
I will
sir.
leave the meeting, sir, because many calls are
Yep.
coming from my office. Okay. Thank you very much. Okay.
Okay. Thank you. Thank you all. And now we shall be moving to our second speaker, who is Mr. Manish Kumar. He is water resource engineer in DHI India Private Limited. And a brief introduction about him is he is specialized in hydraulic and hydrological modeling, urban modeling, and inflow flood forecasting. He has been trainer of Mike Hydro River Basin, Mike Flood, Mike Urban, and also Mike Operation. He also has working experience on ArcGIS, Map Info, InfoWorks, ERDAS, SWIR, CAD, AutoCAD, Loop, and Branch Software. He is a postgraduate in water resource from Terry University and has been member of International Commission of Large Dams for more than 10 years. Thank you, sir, for joining us as speaker. And hello, sir. Hello, Manish, sir.
Hello. Hello. Yes, I can
Yes,
hear
sir.
you. Thank you.
Yes,
And good
thank
afternoon
you, sir.
to everyone.
Yes,
So you can allow me to share the screen.
yes, sir. Thank you, sir. I'm doing.
Yes, sir. We make you as presenter.
Okay.
Hello.
Just 1 minute. It's getting uploaded. 1 minute,
Yes,
please.
sir. Yes.
I hope you can see the screen, right?
Yes, sir.
Okay. So today I am going to discuss about Mike Flood software. Mike is a proprietary software of DHI. I have been working in DHI for last 10 years. So I will give you a brief introduction about DHI and then we will move to model. Okay. So DHI is a Danish Hydraulics Institute and it works in 3 layers. So one of the work is developing water related software, and then we also provide consultancy services, and we also are involved in this academic. So we are on the quest. We are solving almost all the challenges related to water and environment. We are global. We are in more than 35 countries across the world. we are independent, private, and non-for-profit organization. When we say non-for-profit organization, it means that whatever the profit we are earning from consultancy projects, that is used, or that is utilized for development of softwares, basically in research field. So there are almost 1,000 employees. 80% has MSc or PhD degrees. So we work in solution field. We are in the software development field, and then academy by DHI, where we transfer the knowledge, the software regarding the tools and softwares that is being developed by this mic powered by DHI. So we started in nearly 2001, and then till now we have done projects along this India. So starting from Jammu Kashmir to Kerala or Tamil Nadu. So we have done lots of projects regarding to this real-time decision support system for operational management of reservoirs. In this project, personally involved for like 7-8 years, and then this real-time decision support system is basically a sort of inflow forecasting system. And we have inflow forecasting system for Nepal. Also, we have done a lot of morphological analysis, DSS projects funded in this World Bank, and now it's called National Hydrology. Lots of other projects in different parts of India. So regarding this software product, we have this proprietary software related to this coast and sea, water sources, groundwater, as well as the urban model for cities and small towns. So softwares available. So it's like we have surface water model, 1D river model, 2D river model. We have urban model, pipe water flow. We have mic flood, where you can couple 1D, 2D, or urban model. Then we have water quality models. So there are lots of modules available, and it's still in the development phase. Lots of new techniques is being developed by this mic powered by DHI. On this, we are arranging seminars, conferences, and other platforms to share our knowledge. We have training courses. The training, we have open enrollment and tailored course for specific persons, a specific institute as per their requirement. And we have few courses regarding various software, where a person can go to the website and can enroll themselves. Then we have some self-paced training courses. So you can go to the DHI website, and then you can yourself, and then you can learn those models, those tools and techniques as per your timing, as per your requirement. And these training courses are free. Most of the component is free, so you can go there and you can learn software. So we are providing trainings to almost all institutes, NIT, IITs, and this government departments, CWC, and other departments as well. We have trainers in India, as well as we call trainers from Denmark and other countries based on the client's requirement as well as the topics requirement. So regarding these licenses, these softwares are means we have different types of licenses. Professional license is the full suite that is available that you can purchase from DHI. And then addition to this professional license, there are university licenses, which is 50% of the cost is almost 50% of the professional license, but that has to be utilized only for research purposes. Then we have this lab kit licenses, which is almost 10% of the actual cost. It has limited capabilities only for classroom training purposes. And then we also provide a student free licenses for their master's research work as well as PhD research works. So in that case, you will have to write to DHI, giving the details of types of researches you are doing, and with a certification that you will not utilize this for any commercial purpose. So this is a little bit about DHI. Now I will go to this today's topic about this mic flood. So mic flood is a tool developed by DHI. It's a dynamic coupling of 3 DHI models. So it's a dynamic coupling of 1D river model, which is mic hydro river, 1D pipe flow model, that is mic urban, and 2D urban overland flow model, that is mic 21. So mic 1D river model, 1D mic hydro river is 1D river flow model, which is the replacement of iconic mic 11 model, which our previous presenter was also talking about. So mic 11 is well 1D river model. Now DHI has added few tools to mic 1, especially the graphical GIS interface. Plus, we are also trying to make all our modules similar, so that a person who has worked one module, he or she should be able to work on another module as well. So in that direction, we are trying to have the same look and feel of all the modules, and mic hydro river is developed in that process. So mic hydro river is using the mic 11 modeling engine only. So mic hydro river is a 1D river flow model. Mic urban is pipe flow model, and mic 21 is overland flow model. So the mic flood can couple all these 3 modules. It is used mainly for floodplain modeling, storm surge studies, urban drainage assessment, dam break simulations, hydraulic design of structures, and many other applications. So these are the few applications. Now, to do urban flooding, urban flooding actually is a very complex phenomenon. So this urban flooding could be a combination of could be due to combination of fluvial flooding as well as this coastal flooding. So models should be able to simulate all these 3 types of modeling phenomena, flooding phenomena. So fluvial flooding is flooding due to we say river flooding. So when there is some rain in upstream catchments and this flows, it causes flooding in some downstream area due to overwhelming of the capacity of the river. Then it's called fluvial flooding. And when a rainfall, due to a heavy rainfall in a particular area, it causes flooding. When its drainage system gets overwhelmed, then it's called fluvial flooding. Similarly, in the coastal area, due to tides or storm surge, you have this sort of coastal flooding. It could be a combination. A flooding could be a combination of all these 3 processes. Mic flood is capable of incorporating all these 3 flood mechanisms. So a little bit about development of mic flood. Initially, DHI started developed this mic 21, this overland flow model, 2D model, where there were no capabilities of putting structures. So mic 21 was developed with no structure capabilities, On the other hand, Mike 1.1 was 1D river model, and there you could put 1D structure in numerous ways. And then in 2002, DHI coupled Mike 21 and Mike 1.1 to make Mike flood river. Further, in 2007, Mike R1 was also introduced, and now it's three-way coupling system. So you can couple 1D river model to urban model or overland model, and similarly, every model can be coupled with each other. Now, Mike flood concept. So, flooding can be caused due to when your channel or river flow get overwhelmed, its capacity, there is more water than its carrying capacity, then it causes flooding to the floodplain area along the river channel. Similarly, if your sewer or stormwater drainage network gets overwhelmed, it can cause flooding. So it's stormwater flow to surface flow. You can couple Mike 1.1 to Mike 21 in the way that, say, this is a river network. So this is a 1D river network where you have your river network with cross sections. Okay, and then it's a floodplain area. What the releases from these 2 points, which is the coupling points. So from here, the releases from here go to the floodplain area, and you want to see the extent of flood due to the releases from this 1D river model into this 2D floodplain area. So here we are connecting 1D river model to 2D river model through a standard link. Now, why this coupling is required? See, 2D flood model requires lots of time. It requires lots of time to run, and 1D river is comparatively easier and takes very less time to run. So, and the flooding is not everywhere. So, for the area where there is no flooding, we run 1D model, and then when there is a flooding, maybe due to standard linkage or lateral linking, when it causes flooding in the floodplain area, we at those locations only we provide the 2D mapping, and then we get the flood inundation mapping. So there are various ways to connect your 1D river model to this bathymetry information of 2D model. So one of the options that I have discussed already is the standard link, where you connect the end of your river to this floodplain area, and then there is lateral linking. Lateral linking is when you, so this is example of a standard linking. This is lateral linking. When your left levee and right levee of a river causes flooding in the this floodplain area, when water flowing through your river system is more than its carrying capacity. So that's the lateral linking. Now, so you can make a standard linking, you can make lateral link, you can make a structure link. Similarly, when you are connecting Mike R1 to Mike 21, you will be connecting it with inlet point or outlet point, or through weir or pump. You can connect your pipe flow model to this urban overland flow model, means Mike 21. Similarly, Mike 1.1 and Mike hydro river can be connected with inlet or outlet point, that is the manholes or outlet point or any structures like weir or pumping station. So this is example of standard linking, this is a structure linking, this is a side structure linking, lateral linking. So this is a standard cross section which you draw in Mike hydro river or 1.1 model. So here you can see this, you have this left levee as well as your right levee. So when there is water in Mike 1.1 means 1D model, you cannot see the extent of flow in this lateral direction. So whenever you define your left and right levee, it created a boundary like this, this red color boundary. So whenever there is a flow, additional flow to this cross section, it will go along. Means you can see the rise in level. Okay, you cannot see the this its extent in lateral direction. So when you connect this your right levee or left levee to floodplain area, so whenever there is a additional flow in this cross section, it will cause flooding in this direction or in this direction, depending on the means flow available in your this river channel. So this is about linking your Mike hydro river to Mike 21. So similarly, it's like urban linking, manholes. Then connect your manholes to Mike 21. If there is some additional, if there is flooding in your urban area, it will the water will also enter your wastewater or a stormwater network. Or when there is additional water in your stormwater, it will cause flooding, surface flooding. So these are just two examples where you couple means different types of modules. So you connect your river model when you connect your urban model to your river model, so it will act as a weir. Means when you put some manholes there, so wherever the water level rises, that manhole the height, then it will release its water into this river network. Similarly, when the river network becomes higher than the outlet of this the mouth of manholes, the water from river will flow into the manholes, and due to backwater effect, it causes flooding upstream region. So these are the various modules which you can couple in using Mike flood. So you can couple Mike R1 to Mike 21 HD module, Mike R1, Mike R1 and Mike 21 module. Then there is also water quality module which you can couple. So in Mike Hydro River itself, this advection dispersion module is available, which is coupled with Ecolab to do water quality modeling. So you can do the same thing in Mike 21 also. So Mike 21 AD, when coupled with the Ecolab, you can do the water quality modeling in 2D plane area. So you can couple all these three components: Mike Hydro River, Mike 21, this module, as well as this water quality module to the complete modeling. So this is about Mike flood, but these modules means Mike Hydro River or Mike 21 can be coupled with other module or also of DHI, which is like FFlow or Mike C. So the lots of flexibility is available in these various modules, where you can couple one module with other module to do a particular type of modeling. So now I will go about this graphical interface. I will show you here, and then I will give you a live demo. So this is the graphical user interface. When you open this Mike flood, then see, Mike flood is only a coupling tool. It does not have any mathematical engine itself. Okay, it uses the engine of whatever the module Mike flood. Then it has linkage file option. So in the linkage file, you have 2D surface module, river module, and urban module available. So once you select the module, the type of module you want to do, then in the link definition, you will define that how you want to couple your 1D river to 2D river module. So it's about when you have installed Mike flood, then it's a part of Mike 0. So all surface water module is a part of Mike 0 package. So when you purchase any software, Mike Hydro River, Mike 21, or Mike Flood, Mike C, so you are getting actually you are installing Mike 0 package, and then when you open Mike 0 package, here from here in the new file you can open different of modules. So I will go in detail, then I will give you a live demo. So when you open this mic plus, a link file like this will come, where you can take whatever the modules you want to apply, and then if you want to apply water quality also, then you need to take apply AD coupling. Additional information will come here to give you the parameters, associated parameters. So here this way. Now here in the 2D surface module, when you connect this 2D surface model, when you want to connect your 2D surface model here, you click here, and then this 2D surface model has two types of modules available. One is the this rectangular grid, so that is the Mike 21 model, and then you can also provide flexible mesh. So then in that case, if you are using flexible mesh, then you will search select here Mike 21 FM module. So this is a rectangular grid. So it has a fixed shape of this grid size is fixed, and then you have a base DEM or this elevation profiles available with you. So you convert those into a DFS2 file. There are tools available where you can convert your ASCII file or other file format into DFS2 file format, and you can use it here. Then there is flexible mesh option. So based on the XYZ value available for your surveyed value data available, you can create a flexible mesh, and you can use that in 2D over land flow module. Similarly, river model, though Mike 11 has been decommissioned, but lots of projects have been developed on Mike 11. So we are also providing Mike 11 facility here. So you can connect your Mike 11 model or Mike Hydro River model to your 2D model. So you need to select whether you want to connect Mike 11 model or Mike Hydro module. So similarly, you can connect your urban module. Once you have selected the types of module, so in the GIS interface, you can see all the modules available. So here you have this 2D this elevation profile available, and then 1D river model is available. So you can here you can connect your 2D 1D model to your 2D floodplain area. So here this option will connect here. You will get an option to connect your right levee or left levee of this section to the grid Mike 21 grid cell. And whenever this water is there is additional water in that river cross section, it will, based on this flow pattern and this level profile, it will move to Mike 21 grid cell, and it will cause flooding in floodplain area. So that flood extent you can see using Mike 21 model. So this is just an example where you can connect your river module or tributary from a particular chain edge to a different Mike 21 cells. So this connection is very easy. So then I will give you a live demo. You will know how to connect this. Similarly, you can connect your urban module. So you can connect to manholes, various manholes or outlet points to your floodplain area. So you select a particular manholes where you know that it is causing flooding. You connect all manholes. See, it's always a choice. Means how much time you want to give to run a particular model. So if you know that only a particular reach is causing flooding, so if you will connect only particular reach, means running a module will be very quick one. If you will connect the complete module, it's a choice. It will take some additional time to run the model. So all these options and flexibility is available here. Now I will give you a quick demo, and then we'll come back to some additional these pages. So once you have installed Mike 0 package, So you will search here Mic 0. So you will find here Mic 0 desktop app. I hope you are able to see. Yeah. So it's a Mic 0 desktop app. You need to search. So it is available. So whenever you are installing Mic 0 package, so it will, you can find here in this window this Mic 0 2020. So the name of the folder as well as its version will be available. Here you can search and you can go to this Mic 0 app. So when you open this Mic 0 app, so a window like this will open. So here when you will go to this file, and that option, it has option to open new and or open. So when you click on new file, so you can get here all the modules that is available for the to model different types of phenomena. So here we have this Mic Hydro River, Mic 1, Mic 21, Mic Flood module. So different types of modules here. So when you in the product type, whatever the modules you will select, okay, accordingly its files with the associated files you can see in the documents folder. So so you can see when I want to run Mic Hydro, so this Mic Hydro model is available and its cross section files option is available here. So there, and then in Mic C, these are the modules available in Mic Flood model. And then there are some files which is available in Mic 0. So all the modules which you want to use, associated file will be put in that particular folder. And then there are some common files which is used in more than one module that will be available in Mic 0. So this is the structure that we are following. So suppose if I want to open Mic Flood, I will select Mic Flood, and this Mic Flood, if I will double click, so it will open a Mic Flood module. And then here you can see in this file, again, if you want to open file, from here itself you can open another modules as well. So this is the standard Mic Flood page looks like. So here in the linkage file, when you will click on the linkage file, you will have the option to connect different types of module. So when you click on river module, it will get highlighted and you can connect it to various river module. So suppose if I want to connect to Mic Hydro River, so here you can see I have this here. I have option to select simulation file, means Mic 11 simulation file or Mic Hydro River simulation file. So here Mic Hydro simulation file is available, so I can connect it here, Mic Hydro River. Once you have connected your Mic Hydro River, then we 2D surface model or urban model, it's a choice. So if I will connect to 2D surface model, then again I will go here and then I will select for my Mic 21 model. So here again you have option whether you want to connect flexible mesh or Mic 21 model. Say I am selecting Mic 21 model. So this way you can means whatever the modules you want to run, you can connect various modules here. And then in the linkage definition, whatever module I am selecting here, all that based on its this coordinate system, it will open. It will be overlapped on each other. So this is my this red color. This is my river profile, 1D river profile, and in the background is the 2D surface model. So once I have means open it here, I need to link this 1D river model to 2D surface model. If I will right click here it has link river branch to Mic 21. So here you have the option whether you can connect it lateral by lateral linkage, by a standard linkage, by structure implicit structure or side structure. So if I say select, if I want to select lateral linkage, then all the river name, this branch name that is available in 1D river model, that will come here. And then from here, you can select any branch of your choice, and then from which channel to which channel you want to connect your model. So here I have a choice that I can connect only a particular section or my complete river section to 2D model. It's a choice. If you know that a particular section is only causing flooding, you can connect those channels only. Or if you want to see that, if you want to know that what are the areas that may cause flooding, whatever the section, river section that may cause flooding, then you can connect your river section. So here, suppose if I want to connect it to say 5,000 to 6,000, I have a choice here. And then here, how you want to connect your 1D river model to 2D map. Then if you want to connect your left and right levee to your this 2D model, then you select here left and right. Otherwise, you can select left, center, right, whatever the it's your choice. So if I select both left and right levee, I want to connect to this Mike 21 module, then I will select here this. And then if I will zoom to this place, we will see that it gets connected here. So here I have connected from this section to this section to 2D flood model. So all this boundary from here to here, it got connected to your floodplain area. So here basically the number of Mike 21 cells that's getting connected is 147 on the left side and 140 on the right side. So by default, this is the standard by default. So if I am not doing any standard linking, then I need to delete my standard linking. So I have only lateral linking from this channel to this channel. You can see it's the cell coordinate values where this gets connected. It's in the term of J and K value. You can see, if you want to delete a particular grid cell, you can delete further. You can whatever the means, you have full flexibility. Whatever the grid cell you will select here, accordingly it will be selected here. And then you have flexibility that you want to, if you want to delete some of the component further, you can delete it from here also. So once you have connected this, so how this will behave? This left levee or right levee will act as a weir. Okay. So when I go to this lateral link option, you can see this river branches from this channel to this channel connected to this, and this left and right levee will act as a weir. And its formula, this factors have been calculated based on experiences from various projects. So you will not change that unless until you have a research work you want to change and see the impact. There are various modules available. You can provide QS table here, or you can give different types of beer. So here, whatever the module, whatever the connections you will be making, the details you can see here. And then if you have some structure linking, which I don't have, then you will see that it gets highlighted and automatically its value will come here. If there is urban linking, so that option will come here. If it's river to urban linking, that option will come here. If it's site structure linking, so all these are types of linking that you can do with using MikeFlood. So here we are only using urban link, lateral linking of 1D river to 2D river module. So if I want to connect urban module as well, I will be having option here. So if I will go here, then I can connect here urban module. So I am connecting my urban module here. So once you have connected your urban module here, so here you can see, you will get the urban model also available here, and then you will have the option to connect your urban module to river module or to 2D module. It's a choice. So it's an urban model where the discharges from this household or this stormwater drainage network is going to certain river section. So you can connect your urban model to your one model or hydro river model, or you can also connect these nodes or manholes to your 2D module. So you will have additional option where you can connect your urban node to Mic 21, river branch to Mic urban, river branch to Mic option. So all option is available here. And then suppose I want to connect my river branch to Mic urban, then if I will select this, then obviously this option will come. Suppose I want to connect only my outlet point to river model. So then I will have option, then I will select this, and then I have various this module available. Suppose I connect suppose any select, and then I will say get change, and then I will say okay, then a particular node will at a particular change on river network will get connected. So this way I can connect my outlet point, weir point, urban point, or water level boundary. So this way you can connect your urban module as to Mic 11. Similarly, you can connect your urban node to Mic 21. So you can connect all the nodes that is available, whatever the node or outlet point you want to connect to your urban module. Or you can also create a list of node files which you want to connect to your urban this 21 module, or there is an option to connect to all nodes to urban module. This all nodes of urban model to Mic 21 module, you can do it here. So lots of flexibility is available to connect various modules to other modules. So this is about Mic flood module. Now I will go a little bit about all the models that is available and type of data that is required. So here you can open from here also, or you can directly click here, edit different type of modules. Then like if I will click here, edit river module, it will open my Mic hydro river, and then I can modify my river network, can do some editing, and then I can run my model again, Mic flood. So I will go to Mic hydro river now. It will take a little time to open. Just wait. Mic hydro river takes some time to open. It has DM in the background because then its sizes increases and then it takes some time to open. Just wait. So once this river module is open, I will explain you the types of data that is required and the flexibility that is available in 1D river model. As sir has already discussed lots of theoretical background, like the types of equation that it will solve a Saint-Venant equation, kinematic, diffusive, or full hydrodynamic module you want to use. So I will not go into that detail. So I will just give you the introduction about the tools that is available here, which you can define your model in a simpler and easier way. or I can. I will. Actually, one model is running. That's why it may be taking some time. Just wait. Or you can do is I can also open it from here. Okay, it has got open here. So this is a mic hydro river. Here, when you will open this new file, mic hydro model. So when you open this, similar window will come, and where you can define your module. So in the all DHI software has the similar platform where you have all this setup information available this side, and then GIS platform here. All the properties window will come this side, and it's validation, time series, and other information, simulation details you can see at the bottom. So this is the standard DHI look and feel of the any software, and then all these places are dockable. So if you want to move or change, you can do that. So here, so this is about setup, symbology, and result. So you have the setup window, symbology window, result window here. So the color and background information, if you want to change, you can change in the symbology section. And then in the result section, you can see the model simulated result. So I will go into this detail further. So once you will open this mic hydro river in the module section, just a minute. Just wait. So in the module section, you have here this map window as well as tabular window. So whenever you want to put some, if you want to give some data, you can click on tabular window. And then if you want to see your data, you can click on map window. So here in the module, you have a river as well as basin module. I am going only into the river module as of now. And then you have this option, this rainfall runoff module as well as hydrodynamic module. And then for water quality, sediment transport, data assimilation, especially in flow forecasting system. So there are different modules available here, further modules available here. So whatever the modules you will select, like here, you can see if I want to run, if I will click this, none of the module. So only here the setup file, you can see only information regarding simulation specification, map specification, and result specification. So if I will click on hydrodynamic, all the modules, all the files that is required to develop a hydrodynamic model will come here, like river network, its cross section, this hydrodynamic parameter, boundary condition, initial condition. So all this information has come. And if I click on this rainfall runoff module, it's the catchment characteristics, the catchment information will also come here. So here, so this is the way you select different types of modules, which type of module you want to run. So that information is given here. Then another option is from when to when you want to run your model and at what time step. It's very important what time step you want to run your model. Normally, we run 1D river model in the time scale of minutes. We run 2D model in the time scale of seconds, and we run this. If you want to run only rainfall runoff module, then you can run in hourly or daily databases. So that choice is up to you. But the concept is that, say, I will give you. I will give you that example when I will explain Mike 21. Then it will be easier for me to explain. So I will how means what time step you can give for different types of module. I will explain there. Then you have coordinate system, projection system. You all know. I don't need to explain it again. You can add different types of shape files or georeference pages or raster file in the background here. So suppose if you have DM with you for any particular area, you can add your DM in the background layer here. Then in this DM, you can select the type of DM you want to work with, and then there is one tool, pre-process DM. So once you pre-process your DM, and if it's showing here up to date, that means now you can use your DM for river tracing and catchment delineation. So you need not use any high ArcGIS or any GIS platform to get your river network or cross-section files. You can directly use your DM to extract cross sections, or you can do river tracing and catchment delineation directly on Mike Hydro River platform. So that's one thing. Then in the branches, if you will go to branches, so what are the informations required to establish a Mike Hydro River model? So the information required is first river central line, that is the river network map. So river branch name, from where, from chainage means the length of the branch, and its topo ID. Topo ID basically helps you connect to the cross section. So a river here is identified by branch name and its topo ID. So if you will define your cross section for a particular river, so you should have a branch name and topo ID. Basically, we get cross section files from different places, so we save that cross sections under different topo ID, and the final cross section which we with which I want to run my model, I can give the topo ID of that cross file. So this way here, if some branch is connecting to some another branches, or automatic or upstream and downstream connections will come as per its connections. The digitization direction is your river flow direction. So here you can see here, when you will click on map, so here one option is add trace button. So if you have a DM in the background, and then you can use this river trace button. So if you will click on any part of your DM, so from there to the downstream most point, it will give you a path. Okay, from there this river is going where. So if I will select here, and if I have a DM in the background, you can see that it can trace a river down in the downstream direction. Or you can add, if you have some shape file or georeferenced image, Google image in the background, you can digitize this here also using the add button. And then you can edit and merge, delete, other tools are available here. Then you can connect your river one branch tributary to river branch using the branch connection. So these are the tools available in this Mike Hydro River. Regarding this cross section file, here in the tools you have options where you can, using DM, you can automatically generate cross sections for each river branch as per your depth and width choice. So means chainage points means length and width points. So just a minute. If you here, go to this cross section, go to tabular window, and you can see all the cross sections that is available here. So here you give the cross section file, and a cross section file will look here. You need to define your right and left levy as well as your bottom point. So there is a tool here where you can update your markers. You can provide Manning value for all cross sections along the cross sections, different part. So you can provide your resistance number here. You can provide your you can provide uniform resistance value. You can provide distributed resistance value. So that's up to you how you want to define your reverse sections. It's more better the information, better will be your simulated result. So this is the tool auto generate cross sections. So if you have a DM, then you can give at what interval and at how much width you want to generate your cross sections. You can give also locations means where you want to develop a cross section file. So you can create a shape file of change points along the river. If it's not uniform, means you don't want your cross section at equal interval, you want at varying interval, then you can provide the shape file here. If you have survey data, suppose if you have used like total station survey or like that, then basically you will be having X, Y information, X and Z information, X, Y and Z information in your survey shape file. Then you will give a ID file, cross section ID file. You will select ID file and the Z file. And for a particular branch for which that survey has been done, you select and say generate. Then it will automatically generate either from DA or it will take the value from survey. So it will automatically create all these files along the river change point. This topo ID, like if you want to do some modification here in this cross section, so you can copy this ID and you can see it in another ID. You do the modification, change and check. Means because many a times we are mostly dependent on DM to extract cross section, and if your DM resolution is not good, so for various portions you will be getting means bad cross sections data. So you need to update or modify those cross sections, or sometimes there you have a means few locations you have surveyed cross sections, from other locations you have DM cross sections. Then you can you want to update your cross sections extracted from DM based on observed cross sections data. Then you can create new topo ID here, and then you can update your data preserving your original data. You do the modification and then in branches give that cross section topo ID there, and then you can run your model. So this way you can provide the cross section. So once you have river network and cross sections data, again remember, as a previous speaker has also explained, that though you can give cross section 100 kilometer apart, but you should the result will be very you will not get a good result in that case. So here what you need to do is, for your river section, try to cover all those parts. Try to give cross section at least at all those sections where there is some turning effect in the river. So if river profile is changing, you have to give cross sections closer enough to capture those profile changes. So this way you can provide your cross sections data. So maybe for some region where it's it's a long stretch without any turning and turns, you can provide cross sections at longer interval. Where it has turning effects, you can provide cross sections every 1 kilometer, every 2 kilometer, and depending on the data availability and your model. In any case, whatever the cross sections you are providing, here one option is the maximum dx. So this is the dx value is like the interval at which your cross sections, your model will calculate the water level. So dx basically, suppose your cross section is say 1 kilometer apart, then automatically your dx will be 1 kilometer. So in this mic setup, in 1D river model, whatever the cross section points are there, so that will be your calculation of water level points. Okay, and whatever in between those cross sections will be calculated discharge. So like previous speaker has also explained, you get water level at 2 cross sections and you get discharge in between 2 cross sections. So that's how we do the calculation here. It's 6-point Abbott equation that we are using along with the Saint-Venant equation to solve this finite differential equation. So here, suppose I have given say 10 kilometer apart my 2 cross sections. So obviously water level will be calculated at 10 kilometer interval. But suppose here, if I am providing my maximum dx 1 kilometer, then what will happen that during simulation, the model will automatically interpolate cross section at every 1 kilometer. Okay, so whatever the dx you are providing here, it will this is the maximum dx. So if your cross section is say 500 meter apart, and here you are giving maximum dx 1 kilometer, water level will calculated at 500 meter apart only. So the first criteria for water level calculation, it will take from your cross section, and then whatever the information you are providing here, that will be the maximum. Like suppose if your cross section is the same for some section, cross section is say 5 kilometer apart. In that case, for those sections, water level will be calculated 1 kilometer apart. That is the maximum dx. So minimum dx is the cross section value subject to this maximum dx available here. You can provide different dx value for different branches here in the local value. So that is the flexibility available here. Now, once you have defined your river network and cross sections information, you need to that your river 1D river model is ready, and now you need to provide boundary condition. Boundary condition is a standard boundary is your start of the river section, end of the river section. So because it takes the information from the previous channel, as previous slide also explained. So to get a value of dt plus 1, you need to, it will take the information from dt. So it's like a 6-point Abbott equation it will solve. So there means in layman language, I can say like to calculate level at any section, it uses the information means q upstream and q downstream. So similarly, to get information of any discharge at any section, it will use the information level above and level downstream. So here at the start point, you need to define what is the scenario. It could be closed one and it could be open one. Like say, if you want to do a modeling of Ganga River, and if it's starting from Gangotri and to ocean, then your starting point could be closed one. But if you are starting your model from say Allahabad to Varanasi, then obviously at your model boundary, start of your model boundary, there is some already inflow there in the river. So whatever the component that you are not modeling for, that you have to provide a boundary condition. So start then in that case could be open one, and then you can give the additional discharge that is entering into your modeling system, or water level, or say if some rainfall component is there, then you can also provide those information. So these are the options. Normally we provide water water level or discharge at the starting point. Similarly, your model is not ending at Varanasi. Okay, so what will be how the water will leave after your that model boundary is ending. So we need information afterward. So there you can give various informations like, number one, if it's entering into sea, you can give constant level, because discharge from a river will not change the ocean level. So you can give a constant level. You can give a free outflow. You can give a QH relation. So if your end point is important, okay, for your that modeling component, then you give a QH relation at the end point. So if you will select a QH relation, it will automatically calculate the QH relation based on the cross sections file you have given. So cross sections file, till your model end, that slope and everything is given. System does not know the slope afterward. So if you will calculate QH, it will ask for a Manning formula. That is the information afterward the last cross section file. It is at the end of the river process file. So that information, if you will give, it will automatically calculate the QH based on the cross section file that you have already provided in this cross section module. So once you have done that, so for each river network, basically you will have two boundary conditions, starting chainage and end chainage. But suppose your tributary ending into the river, then it will have only one boundary condition. Another boundary condition, it will automatically take this system. So accordingly, define the boundary conditions. Any additional information which you are not modeling for, like discharges from some industrial area going to some river, or if there is some uptake of water from river sections for irrigation or other purpose, you can provide all these informations in the boundary condition for a particular change. So that's way your 1D river model is ready. Once your 1D river model is ready, then you can run your model and you can see the result. Now in the module, if you also want to do this rainfall runoff module, then here that option is here. So basically there are various modules available here. Like for rainfall runoff model, we mostly use NAM module. NAM model is a conceptually lumped model. So when I say lumped model, obviously for a particular catchment, you need one type of data, one data like one rainfall for a particular subcatchment, one evaporation data for a particular subcatchment, and the result will be one catchment discharge for each catchment. So it's a lumped model, not distributed one, but it's a conceptual model. So when I say conceptual model, that means it uses the actual physical phenomenon. Okay, so all the process that when there is some rainfall, some abstraction will be there, some evapotranspiration will be there, then the water, surface water and ground this soil interaction will be there. It will create different storage, subsurface storage, top surface storage. Then there will be groundwater flow, which leads to base flow, and then overland flow, which will cause which mainly causes flooding. So all these components will be modeled based on this parameter. So all these parameters you don't go on field actually to measure, but you calibrate your model based on some historical information. So this is about NAM module. I will not go into the details of NAM module here. But there are other modules also, like UHM, time area, kinematic wave equation. So there are other modules also available, but we mostly use NAM module. It is well established for Indian condition. It gives a very fast result, means results generated very quickly, and it has been tested and used in many inflow forecasting systems, including this inflow forecasting system for the Satluj and Bias River. That is the forecasting system on Bhakra and Bong Dam. So, and there are various reservoirs for which this inflow forecasting system has been used using this NAM module. So, this is about this 1D river model. Here you can see the result file, whatever the result file generated, you can see here. You can click any module, you can select the water level discharge from here, and then you can plot it here also. So you go here, any point you can click, and then you can say add to new plot. So you can get a plot like this. You can select water level or discharge you want to plot for whatever the river branches. But the best way to see the result is in the result file. You can open this result in the using mic view. So just I will open one result. Let me see if I can open. Oh, okay, sorry, I think model is running right now. So that's why you cannot open it here from here. So I will open some other result file. So let me. So once you will open this result file, you can click there on the result file, and you can open it here. And then once you will open it here you will get the option whether you want to see water level discharge, wherever you want to outflow. If it's connected to your mic 21, then left lateral outflow to mic 21, right lateral outflow to mic 21. So how it's going to mic 21, you can see the list at different channels. You can see the result file. You can also click at various sections to see the result file. Then this is the L section. You can see the L section. You can see your result in the L section, like water level, and then you can run your simulation, and then depending, since it's only 1 hour, so one time step only. So if it's a multiple step, then you can see at what time step what is the discharge going. This is a flood scenario generated especially for a particular period, for particular hours when it's actually causing the flood. So for that time only the result has been created. So here these are some of the capabilities available. You can also click on particular cross section, and then you can run your model to see how this water level is changing. Here in mic hydro river, you have the option at what time step you want to run your model. So normally you run on a minute basis, but you also have the option at what time step interval you want to save your result. You did not need to see result every 5 minutes or every 2 minutes. You can save your result every 1 hour, every 3 hour, or per day, depending on the type of model you are using. So this is about 1D river model. Now I will go to 2D river model. So here, sorry. So this is about 1D river model. I will close this 1D river model. I think I have some time left, 15-20 minutes.
Yes, sir.
Yes, sir.
Okay. So now I will just give you a brief introduction about 2D model. So similarly, 1D model I open from here. Then similarly, I will open this 2D model from here. So here in the 2D model, here I am using this rectangular grid information, not flexible mesh information. You have a choice. You can use both type of model. So here, Mike 21 model, the data information that required is huge, but model establishment is quite easy, in the sense that only you need this DFS2 file, means bathymetry information, like this. Like this. So you have 9 meter by 9 meter grid, and for each grade you have certain elevation values. So anywhere you click and you can see the elevation values of those areas. So basically, whatever the this elevation values available with you, means the DM that is available with you, you can convert those DM into this DFS2 file using, there is one tool in this My Zero toolbox. So in this My Zero toolbox, you have option to convert various file formats into other file formats. So using that tool, you can convert your base DA, whatever the highest resolution DM available with you, can convert that to. So here file can this GIS. In the GIS, you have grid to mic, so you can use this to convert into this. Then the mic to grid you can convert, mic to shape, mic to test, shape to XYZ. So all this information is available here. You can, using this tool, you can convert to ASCII file format, that is grid to mic, and you can convert it to DFS2 file. So that is the base information that is available. Then obviously, if you have more and more information, you can apply the, let's say, if you have a building shape file for your area and with its elevation value, so in those particular grids, you can update the elevation values based on the building elevation values. So you can modify your information. If you have your road network or some railway track or something with elevation little higher or less, then you can update those values. So better the information that is available here, elevation every 9 kilometer by 9 kilometer grade. So you can use here. The best way to use is like if you have survey data like XYZ value for information and line profile for river track, means railway track or highways. So you can provide those information. It will help in the sense that suppose some highway is there and it's a little higher elevation, then when flow is moving, it will be causing flow only on the one side of the of that highway, because the highway is at higher elevation and it will act as a weir, means like all the flow will be in one direction only until flow is higher and it crosses to other side. So better the information available in your bathymetry, more high quality flood inundation mapping you can generate. So this is about base map. Then again, if you are using Mike 21, this standard grid model, then you need to provide land boundary. So basically, land boundary is the closed boundary. So obviously, there will be some area here, some grids here, which will never participate in flooding situations. Like maybe if you don't know, like say maybe the flood here does not cross a 100-meter depth, so it never causes flooding, which is at an elevation of say 100 meter or above. So I can provide 100 meter as my land use land boundary, or that information I also provide to close my boundary. So all starting this point, it should be closed boundary. It will be a closed boundary, and then this internally also, inside also, for all those elevations which is not participating in the flood depth, then I can give that a land boundary. So it will further decrease my model calculation time. So that is the one information here. Suppose if you don't know that whether it will cause flooding in the upstream region or not, with the higher elevation or not, if a river is flowing from here, whether it will cause flooding here, or you want to see, then you can provide a higher elevation value. Highest elevation value available, you can provide that as a land boundary. So once you do that land boundary, now here it's important. It's important. Suppose some river is entering here. Suppose some reservoir is here at the end of your at the one boundary, and the flow from that reservoir, release from that reservoir, is entering into this 2D model. And if there's some excess releases from reservoir, you want to see the flood inundation mapping. Then for these grid cells, I can give the actual elevation value. I can make it an open boundary condition. So if this is the open boundary condition, then flow can enter from here into this area and can cause the flooding here. So I have a choice whether I want to keep my boundary open for a particular. Obviously, there will be only few sections through which this river is entering into the system. So there I can keep my boundary open. So that is one thing. Also, we can provide here. I will go to this model now. Just a minute. So in this factory, I can give the land boundary, and in the boundary condition here it's closed one. So if some of the grid cell is having values less than this land boundary, then it will you can see all those grid points from where to where it's open. You can see the value here. Like if I give somewhere I give certain value, then I can see the boundary. Means for those area I can keep my boundary open. So once you have given you have entered your bathymetry, then you need to do it for inlet flooding. So depending on in mic flood, you don't get the full flexibility. But if you are doing some tidal modeling or some sea modeling, then you can use other module as well as you can do this water quality modeling. If normally that when there is some flooding scenario, then the water also have lots of mud or debris like say silt with it, and that impact, then the havoc is more downstream when it carries lots of silt with it. So that's why then in that case you can also include that module also if you want to see the impact downstream due to this silt coming along with this water. So that module is available. Then this is about boundary. Now source and sink is like inside your land boundary. Like say if you want to see if you will put some water in some of the grid cell, then how the spread will be. Like say if there is some precipitation in your this area in some grid cells, say 100 or 200 grid cells is having certain precipitation impact, then you can increase that. You can give that means isolated places area, this x and y value you can provide here, and then this way you can create source and sink where you can provide precipitation and evaporation information, and it will show you the impact of flooding due to precipitation impact. Remember, it will only show you, it will not consider the soil component, means the water that is initially water that is going into the soil absorbed. It will take all the water as overland flow and then will show you the extent. So this is about source and sink. So once you have defined your boundary or source and sink here, then here in the boundary accordingly, if it's closed, then nothing option will come. If it's open, then for here you can give for all value. You can give time series or constant value here. So you can give some time series also. then you can means for different section, or you can give say if what will happen if 50 rainfall is happening in your catchment area. So that value you can provide here. So similarly, you can provide the infiltration, eddy viscosity, resistance, manning number, and then you save your result. Whether, again, it's important here what type of information you want to see in result. You can go here and then just a minute. Yeah, you click here and then you want to see depth, elevation, velocity, still water there, for fraud number, speed, stress, velocity. So all this, whatever you want to see, you can tick here. You can see. Remember, whatever the more the module you will select, it will increase the size of the output size. Again, similarly here also, whether you want to see your result along X and Y direction in all the grid cell, or you want to interpolate two grid cells to see one result, you can do that. So you can keep it will again decide the size of your output file. This is important because you are running your model in seconds. Do you want to see the result every second? No, you can see your result every minute, every 5 minutes. So in that case, you can decide at what interval you want to see your result. Now I will go to this component which I left in previous, like what is the time step. So it's I will try to explain it in a say simpler manner. Is like say your model is having say 1 meter by 1 meter grid size, and the velocity in water, the velocity of water in grid 1 is say 1 meter per second. Then how much time it will take to reach to grid 2? 1 second. So in 1 second it will reach from grid 1 to grid 2 if your grid size is 1 meter. 1 meter. Now you cannot, if you will run your model say every 2 seconds, then what will happen? The water from grid 1 will reach grid 3. Okay, so there will be no calculation for grid 2 and your model will stop. It will give you an error. So if your velocity of water, if the velocity of water is 1 meter per second and grid size is 1 meter by 1 meter, then you cannot run your model every 2 seconds. You will have to run your model every second. That's the simple explanation. The detailed one is the current number, but the simple explanation is this, that now you increase the grid size. Increase the grid size by say 3 meter by 3 meter. What will happen? If the velocity is 1 meter per second only, then in 2 seconds, the water will be in grid 1 itself. It will not reach grid 2. Okay, so it will, so you can do the calculation. Like if your grid size, if you will increase the grid size, then every grid cell value will be calculated. Okay, so one of the options, if you get an error, is that either you increase the grid size or same way you decrease the calculation time. Like if your grid size is 1 meter by 1 meter, velocity is 1 second, then you will have to run your model on 0.5 second or up to 1 second. You cannot run your model more than 1 second. So either you decrease your time or you increase your grid size so that your current number is not more than 1, and you could be able to run your model. Similarly, in 1D model also, if your cross section is say 1 kilometer apart and the velocity is 1 meter per second, then you see how much time it will reach from one cross section to another cross section. If your calculation time is more than that, then you will get an error. Your calculation time must be able to do the calculation at each grid point or each cross section point or each DX point. So that's the concept about means what is the simulation time period you can give. So that's why if you are running your model at higher resolution DM, you provide a smaller time step. In 2D model, normally we run in seconds. 2D model, 1 second, 2 seconds, 5 seconds, 20 seconds, depending on the model type. The 1D model we run in minutes, 1 minute, 2 minutes, 5 minutes, depending again on the size and size and dx value of your model. So this is the concept regarding Mike 21 model. Once you have established your Mike 11 model and Mike 21 model, you have made the connections here, then you can see the result. Again, remember that here we are doing all the connections. We are not saving the result anywhere, because whenever we am running this model, this Mike 11 and Mike 21 model result will get updated. So it will run here. It will run both Mike 11 model and Mike 21 model again, and we'll see which are the area where it's causing flood, and there only it will show you the flood inundation mapping. So similarly, I don't think I have much time left, so I will just similar concept with Mike urban model. You can open your Mike urban model. You can establish the manholes. You can give the underground pipe dia. Its capacity you can find. You connect your Mike urban model to Mike 1 or Mike 21 module, and then once your this module is created, then you can run your model and can see the result. Just I will just show you the look and feel of Mike urban module, and then I will discuss with you the result file. So when you open your Mike urban module, so it looks something like this. It's the same structure and feel will remain the same. I will not take more than 10 minutes. Just give me 10 more minutes.
Yes, sir. No issue.
It's a huge model, so it's taking some time to open. This model that I have discussed with you has been created for this Guwahati region. So till this model is opening, I will show you the result file. Just let me see if it's open or not. So I will just okay. It has opened. So it has thousands of manholes and connections and catchments. So it's taking some time to open. A very detailed model. So here in this module, you can see that you have the option select collection system or water distribution system. So the flood situation means for flood modeling, you are taking collection system. This collection system could be means only wastewater underground wastewater system, or it could be a combined system, means wastewater as well as stormwater drainage network. So here, just one more minute. So it's taking some time to open. I will just show you this result first, and then we'll come to Mike urban. So the type of results that you get means the Mike 21, when you run your Mike 21 model and then when you see the results, you get a result something like there. So whatever the module you have selected in the result file, you can see result here. So so when you will open a DFS2 file, it will look something like this. And here, from here, you can move the time step, and you can see the time step here, and then you can see the depth, how it's increasing or decreasing at different interval. You can see the results here. So here you can see your result, how the spread is. But this result is not basically interpretation is not that much here. So you can put some background layers if you have. Then you can see a particular area or shape files. If you have a building shape file or something, so you can put it in the background and you can see whether that how much area is getting inundated. So this is one thing. You can see the result here, but there is a tool here which you can convert this result into Google Earth image result, and then it will be very easy. So this is, and plot this result using Mike to Google Earth. You will get with this Mike flood, Mike to Google Earth. So Mike to Google Earth tool is there. You can use this to convert your DFS2 file result into that result. And when you will open this Mike 21 result file, then I will close this and then open it again. Just a minute.
No, sir.
Yes. So I will just delete everything, and then I will go to, I have created one result file for you. So I will just explain that. So when you will convert your result file into Google Earth image, you will get a result like this. First time, if you are doing this, first you to run it one time full. So it will plot the result on the Google Earth, and then you can run your simulation quite good. So I will first run it here one time. And then this is a tool where you can run it like this. So I will zoom to a particular area and we'll see the impact of flooding. So you can see at time is changing. It has been developed for a particular event on 27th of May. So the rainfall started on 27th May, and it causes flooding in the morning 5 a.m. to some of the area of Guwahati. So due to this fluvial flooding. So this discharge from river is causing flooding in this area. So here, if I will zoom it further, here few of the building elevation is also given. So it again depends on the quality. Like since building is here, so it's going along the building, leaving the building, and the other area, gardens and everything is getting flooded here. So you see, this is one. It's a rough, like a building like this grid has been given certain elevation profile. So you can see that some of the area is getting flooded, and some of the area is depending on the quality of your this DM, how much detailed information you have provided. You can see the flooding extent in which direction, and how much you can see the depth of water along the time and along the river. So at what time step it's causing flood in a particular region, and how it's receding back at the time process. So all this information you can see. You can create a flood map like this. So this is a small demo of this Mike flood module. Now the DHI is developing a Mike Plus module that will have capabilities. It means one platform where you can do both urban modeling, river modeling, 2D inundation mapping. So all these models will be available on one platform. So DHI working in that direction, and it will be available soon. So that is the future. This information is very important. This is not some historical information, but it is based on inflow forecasting system. Inflow forecasting system is like you have 1D river model, and you have forecasted precipitation information. Forecasted precipitation information you get from various agencies like IMD, NCMRWF, GFS. So they provide quantitative precipitation forecast grade-wise, okay, for your area, and then you use those forecasted precipitation to get forecasted runoff in your river sections. And once you have this forecasted runoff, then you can see along the river if that flow will come, how much area, if that is causing flooding, then how much area will get inundated and which area will get inundated. Once you have this information, prior information, even if it's say 72-hour forecast, that is the best quality we get. 72, though we do have 10 days forecast, but the quality is better in say up to 3 days forecast. So even if you have 3 days prior information of which area will get inundated due to a particular event, and if it's state disaster management, national disaster management, and other local bodies is informed about this, evacuation, saving lives or livestock, all this will be very easy. And then it will cause, means it will save something. You are not going to stop flooding in this case, but you can minimize the impact of flooding if you have this information. Thank you. This is about Mike flood. Now, if you have any query, you can ask me.
Hello, sir.
Yeah.
Am I audible, sir?
Yes.
Hello?
Yes,
Sir,
I can hear you.
Yes, sir. Wonderful demonstration, sir, of Mike software. One query is, sir, where to get the data set for the input models?
Yeah. So, I say that you can start your model, this 1D river model, with your DEM available. So normally 30-meter DEM is available free of cost. Extra 30-meter DEM is available free of cost. So you can extract your river network. You can extract cross section in Mike Hydro River. You can use the same SK file, this 2D model, to create your 2D bathymetry file, DFS2 file for your 2D model. So that is the very first step where you establish your model. Now, obviously, the result quality will not be that good if you have this low resolution DM information. If you have surveyed information or some surveyed cross sections in between, then it will modify the it will update modify your result quality to a greater extent. So you can start your data. There are lots of agencies, like if you are working on river sections, model like CWC has discharge data all over India for various river sections. Then IMD provides this rain gauge information. You can get those information from there. Then there are agencies which provide it free of cost, like you can get the rainfall from IMD website free of cost. You can get NCMRWF forecast, IMD forecast, GFS forecast free of cost. These are available free of cost on their FTP server. So you can download those data from there. You can establish your model using those information. So you can always start your model, and then you can do quick little survey. Means you can get the information from Google Earth Pro, like building structures. You can also provide information like, if it's a means 2-story building or 3-story building there, then you can give some means height, like 5 meter, 10 meter heights to those grade values where you have those building profiles. So you can create shape files from KML file and shape file using Google Earth Pro. You can create a building shape files. You can give the elevation values there. You can update your this downloaded DM using those informations. So this way you can get information from various sources, and you can update your model with whatever information you have. Ultimately, surveyed information is the best information that you need. Yes.
Sir, another query. Just can mic model be decoupled if not in use?
Yes. So see here means even if you are coupling your model, you can run your model individually. Means mic Hydro River, mic 21 model, mic urban model, all run individually. And then if you want to couple one model to another model, then you can couple. And whenever you want to use it individually, you can use it individually as well. So it's up to you. It's completely flexible in that sense.
Thank you, sir, for answering the queries. We have more. We'll mail you, sir, and more queries we have. Now, I shall request my colleague.
Hello. Hello.
Hello.
Hello.
Audible to you, sir?
Hello.
Hello, Manoj, sir?
Hello.
Good afternoon to one and all. Esteemed principal sir, respected advisory committee, organizing committee, faculty colleagues, persons directly or indirectly part of this program, and all our dear participants. It's my great privilege to have been asked to propose a vote of thanks on this FDP program. I, V. Manohar Reddy, on behalf of Civil Engineering Department and the convener of this program, extend a very heartily vote of thanks to all. Respected Principal Sir, Dr. Dolu Patnaik Sir, our beloved principal and patron of this FDP program, who is blessed us with his gracious presence and took out his valuable time in his busy schedule to be a part of this FDP. Thank you very much, sir, for being such an impactful leader and motivating not only our students but also all the faculties over here. Next, I will extend my sincere thanks to Dr. Kishore Chandra Panda sir, HOD and Department of Civil Engineering and chairman of this program. Thank you, sir, for leading us to conduct such a successful program. We would like to see our department conduct such more programs under your guidance, sir. Next, I extend my warm thanks to Dr. Chittaranjan Das sir, TechWeb coordinator. Thanks a lot for never making us feel of financial crunch to organize such a wonderful FDP even in this pandemic situation. Thank you so much, sir. Next, I will extend my thanks to advisory committee and organizing committee for your untiring efforts to make this program happen and sharing the experience to conduct this FDP more smoothly. Next, I extend my thanks to Mr. Saujanya Kumar Sahu, convener of this FDP program. Thanks a lot for being more as a friend rather than a co-convener and helping to the best to make this program a success. Next, I extend my thanks to Mr. Jajati Kesri Naik, sir, Assistant Professor, Department of Civil Engineering. Thanks for your invaluable help to conduct this program very smoothly and a helping hand like a big brother in a crunch situations. And I will extend my thanks to Professor Dilip Bagal, sir, for your invaluable help to make this event smoothly on digital platform. Finally, thank you all the participants for your patient hearing. Knowledge sharing is something that never stops, even this COVID-19 crisis. Thanks for being part of this academic endeavor. With this, I am closing this vote of thanks and now request our beloved HOD sir to say a few words about this conference.
Good afternoon to all of you. So I am very happy to say that more than 170 participants are attending the online seminar in GoToMeeting platform, and also some participants attending through YouTube live streaming from every corner of India and made the online seminar a grand success. I would like to express my big thanks to all the participants who have watched the two sessions patiently. I expect all the participants have gained some information knowledge from the two valuable and informative sessions. I would also like to thanks to our two esteemed speakers, Professor C. Madhusudan Rao and Engineer Manish Kumar for their very valuable demonstration on mic software and that modeling, how to do the modeling and informative presentation on the topic. I would like to thanks to our principal sir for his inspiration and motivation for organizing the program and made it a grand success. Also, I thanks to our TechKeep coordinator for his motivation and financial help through TechKeep and made the program a grand success. Also, I thanks to my departmental colleagues. Their presence and support made it a successful. Also, I thanks to all HODs and the colleagues of other departments and thanks to uh, Professor Dilip Kumar Bagal and Professor Jadati Kesari Naik and Professor Gopal Charan Behra, Professor P.K. Muduli for their help and made the program a grand successful. At the end, I would like to thanks to our two convener of the program, Professor Saujanya Kumar Sav and Professor Manohar Reddy, for their hard work and effort since 15 days and made the program very successful. At the end, I would like to say in coming days also we'll arrange similar program in different topics. Thank you very much. Have a nice day.
Thank you, sir. Now we will be closing the webinar. Thank you all for your encouraging participation. Thank you.
Central.